Welcome everybody to part 2 of the video exercises in taking complex square roots. This here is a pretty difficult exercise. You need to prove this formula. It's completely okay to skip the proof and simply look at the examples. This here is not as frightening as it looks at first glance, but this here is a formula that tells you how to build complex square roots in Cartesian form. This is sometimes easier when you don't have a calculator than transforming it in polar form, as we saw here in this example. For this you absolutely need a calculator to do the arctangent and the transformation back into Cartesian form, whereas here, as we are going to see, it's possible to do without a calculator without any problems. So, given is any complex number z equals a plus bi, a and b, the real and the imaginary part, both real numbers, and then the square root, meaning the solution of the equation w squared equals z that lies here in the upper slotted half plane, is given by this expression. Here we take the real square root of this expression, absolute value of z plus the real part divided by 2 plus the real square root again of absolute value of z minus the real part divided by 2. These are both real roots because here the guy under the root can't be negative because the absolute value plus or minus a, depending on the sign of a, is never a negative number. So here these are well-known roots in the real numbers. And here in front of this, of the real part of this guy here, we have the sign of b, of the imaginary part of our number z. This is defined to be plus 1 or simply a plus sign if b is non-negative, and it is minus 1 or simply a minus sign here if b is negative. Okay, now we're fighting ourselves through the proof, but as I said before, it's okay to skip forward and look at the examples. Or if you want to, you can pause the video now and do these examples here so that you get used to this formula. This would also be a good idea. Oh well, actually, I'm gonna do that now myself, so you can skip the end if you want to, but of course I'd prefer it if you watch this beautiful proof here till the end. So let's start doing the examples, getting acquainted with this formula, and then we are going to prove it. So we start with a simple example, the square root of minus 4. We already know the result. This must be 2i, but let's see if we can reproduce this using this formula here. So minus 4 is minus 4 plus 0 times I. So the absolute value clearly is 4. The real part is minus 4, and the sign of the imaginary part, which is 0, is to define plus 1. So here in front of this first root we write a plus sign. So this is plus square root of absolute value plus a. So we have 4 plus minus 4. So this guy vanishes. This is 0. Then we have plus the square root of absolute value minus a, which is 4 minus minus 4 over 2 times I. This is 8 over 2, so we have to calculate. So this here is square root of 4, which is 2. So we end up with 2i. Very good. Now, of course, for this, it is necessary to use this monster formula, but it's a good way to get acquainted with the terms. Now, this is interesting because, as I said before, to do this with polar form, you need a calculator. Now we see that this is possible without calculator. The absolute value is the square root of 25, this squared plus this squared, and then the square root. So the absolute value is 5, a is 3, and the sign of our imaginary part, which is minus 4, is a minus, so minus 1. So here I write a minus sign in front of this square root, and then I end up with this expression. And now here I have 8 over 2, which is 4. So I have square root of 4, the real square root, which is minus 2. Minus square root of 4 is minus 2. And here I have 2 over 2, which is 1. So minus 2 plus I. And now you have to agree that this solution, of course, is way more elegant and doable than to use the polar form. So this is one of the uses of this formula. Now a good exercise for yourself would be to pause the video and to verify that the square root of this here is indeed 3 plus 2i. And of course, if this is an exam question, the numbers will always be chosen so that you can actually calculate the absolute value and the square roots. But here again, without calculator, it's not possible to do this in polar form. All right, now for the proof of this splendid formula. So by definition of square roots, we are looking for solutions of this equation here. W squared equals this given z, so a plus bi. So we write the w, the solutions we are looking for, in the form x plus yi, x and y real numbers. So I square using the binomial formula, and here observing yi squared is minus y squared because I squared is minus 1. So I have as a real part of this guy here x squared minus y squared, and the imaginary part is 2xy. And this must be equal to a plus bi. So after comparing real and imaginary parts, I end up with this system of equations. If I can solve these for x and y, I have found my solutions. Now, if I would have done this by myself, I would have made a lengthy calculation and maybe arrived at these formulas, but there's a more elegant way that I borrow from one of my favorite math books ever, Königsberger Analysis 1. Very elegant solution. Again, it uses this almost trivial fact that the absolute value squared is the same as the absolute value of the number squared. So we have w squared is equal to z. So this implies that the absolute value of w squared, which is the same as w squared and then absolute value, we proved that way back when introducing the absolute value. And this here is the same as the absolute value of z, because if I take absolute values here, I have this equation. And now the absolute value of w, of this number, is x squared plus y squared. And we know that this is equal to the absolute value of z. And this here is already in this formula I want to prove. So here I stop here. I do not write this as the square root of a squared plus b squared, but simply let it stand here. Now, if you either add or subtract these two equations, y squared or x squared cancels, and you are left with an easy equation to solve for x or y. So when we add these equations, y squared cancels, and we end up with 2x squared equals absolute value of z plus a, and this I can easily solve for x, and this gives me already this part of the equation I want to prove, but of course with two signs, because I take the real square root. So I end up with a plus and a minus sign. I abbreviate this with plus minus hardsuit. And if I subtract 1 from 3, then x squared cancels, and I end up with an equation for 2y squared, which I can solve in the same way, again with two signs in front of the real square root, and I abbreviate this here with plus minus diamond, or diamond suit. So far we haven't used this equation at all, and this tells us which signs are correct, because we want to end up with one complex number, the error of which lies here in this shaded region, the slotted upper half plane. So we start with a case where the imaginary part of this number is positive. Then by equation 2, this product must be positive. So x and y must have the same sign. I denote it like that. X, y, this pair must have the sign plus plus or minus minus. Now, if this would be correct, minus minus, my solution or my square root would be of the form minus heart minus diamond times I. Diamond itself, the square root here, is a non-negative number, so the arrow of this guy would point downwards, thereby not lying in the upper half plane. But by definition, the square root must lie here, so this is the correct pairing of signs, plus and plus. And if you look here, this fits because the sign of a positive number is plus 1, and indeed we have a plus here, and here we always must have a plus. Now the next case, b is negative. Then by equation 2, x times y must be negative. So the correct sign pairing would be plus minus or minus plus. By the same argument as before, here with plus minus, I would end up with an arrow that points downwards, which can't be the complex root. So this is the correct pairing. And again, this minus here comes from the sign of b, because the sign of b is defined as minus 1 if b is negative. And here again, this plus is also correct. So we end up with this formula. The only case that is left is b is equal to 0. Well, for this case, we could say from the start, this is not very interesting because then z is a real number and we actually already know what the square root is. But even this special case is contained in this beautiful formula if you define that the sign of 0 is plus 1, because then if b is equal to 0, z is, as said before, a real number a. So the absolute value of z is the absolute value of the real number a, the real absolute value. And we already know from before that when a is non-negative, the square root of z is simply the real square root of a. This is defined in the real numbers. Whereas when a is negative, we end up with the square root of the absolute value of a, the real absolute value, times I. And now let's see if this formula gives us the same expression. Indeed, if a is non-negative, then we have here 1. As I said, the sign is defined to be 1. Here the square root of absolute value of a plus a over 2. But the absolute value of a is simply a because a is non-negative. So here we have 2a over 2, which is simply a. So this is the square root of a. Here these guys cancel and this term vanishes. So we end up with the square root of a. And for negative a, here now this expression cancels because for negative a, the absolute value of a is minus a. So here we have 0 and here we have minus a over 2, which is minus 2a over 2 or minus a, but minus a is simply the absolute value, and again we get the expected result. So this formula contains all the cases and automatically gives you the right solution with an arrow pointing upwards, so lying in the upper half plane. Now in all these calculations you can't be absolutely sure if you did equivalencies. So in the end it's always good, whenever taking square roots or squaring is involved, in the end it's always good to check that your solution is actually a solution. So you should check for yourself that here the sign b times heart plus diamond I indeed satisfies this equation. So if I square this expression, you should end up with c. Please do that on your own. Whew, all right. So even if you didn't get every step of this proof, at least you should be able to apply this formula to actually calculate complex square roots in Cartesian form. That's it for today. Thanks for watching and bye-bye.